Hi guys, welcome back. Today we're going to do search a 2D matrix. So we're given an m by n integer matrix called matrix with the following two properties. Each row is sorted in non-decreasing order, so basically just increasing order, and then the first integer of each row is greater than the last integer of the previous row. So basically all they're telling us here is that the matrix is sorted first from left to right and from top to bottom. So given an integer called target, they want us to return true if target is in the matrix or false otherwise, and we must write a solution in O of log of m times n time complexity. So if we take a look at example 1, we're given this matrix and target equals 3, and we would output true because as we can see here, 3 is in the matrix. In example 2, we're given this matrix and target is 13, and we would output false because as we can see here, there's no 13 in the matrix. So if you guys haven't caught on already, we're basically just going to be doing a binary search because anytime you have it sorted and they say it has to be in log runtime, it's basically going to be a binary search. The only difference here is, so like normally in a binary search, you would just, like it is meant for a 1D array, but because we have a 2D array, or like a matrix in this case, it's going to be a little bit more complicated. So I've already gone ahead and copied and pasted example 1 over here to the right. This is the matrix that we were given as input, and I've also gone ahead and put the same array but just like laid out as a 1D array instead of a matrix with target is 3. And so as we can see here, so this is the, like I just did like the rows, so this is like the first row, the second row, and the third row, right, as we can see here. So if we lay it out as like a 1D array like this, where it's like this one first, then this one, then this one, then it's just like a 1D array but sorted, as we can see. So we can't actually create this array though, because if we do, then that's going to mess up the time and space complexity, because in order to create this array, it's going to, first of all, need to store every single element again, which is going to be m times n space, which is not ideal, but like also to even create this array and store all the elements, like to copy all the elements from the matrix over into this array, that is also going to be m times n time complexity already, because we need to traverse this matrix and visit every single element exactly once to even put it in this array. So that's not going to work for us. So we'll sort of reference this, but in our imagination, instead of actually creating the array, if that makes sense. So I'll just have this here for us to reference, but without actually creating it. And then we can just do a binary search, sort of converting back and forth between the two. So like from our imagination array to like the real matrix and back and forth. So to do this conversion, we're going to, so if we have an index I in the 1D array, that is going to convert to the matrix at I divided by n, I mod n, where n is the number of, so it's, if this is an m by n integer matrix, then m is going to be the number of rows in the matrix, while n is the number of columns in the matrix. So we're doing this calculation based on number of columns. So in this case, n is going to be 4, because we have 4 columns, right? We have, well, okay, this is 0 index, but if we count how many columns there actually are, there's going to be 1, 2, 3, and 4 columns. So just as an example, let's say we have index 5, and we want to convert that into whatever spot that the same element, which is going to be 11, is going to be at in the matrix, right? So if we do this calculation, then it's going to be I is 5 divided by, we have 4 columns, and then 5 mod 4, which is going to be matrix at, so 5 divided by 4 is going to be 1, and 5 mod 4 is also going to be 1. So it's matrix at 1 at 1. So if we check row 1, column 1, that is 11, so that works. So let's do this again, but with, let's say index or element, let's say we want element 23, right? So that's going to be at index 8. So index 8 is going to be matrix at, and I is 8, so 8 divided by n is 4, and then 8 mod 4, which is going to be matrix at 2 at 0. Why is there an extra? There we go. So matrix at 2 at 0. So if we check row 2, column 0, that is 23, which is the element that we have at index 8 in the original, or in the 1D array. So that's how we're going to convert back and forth. I'll leave this up here, but I'm going to delete the other ones for just so it looks a little bit easier to find things. So now we can start writing our algorithm. So I'm going to start out by just actually defining m and n, so we don't need to keep referring to things, because like in this conversion it's going to be easier if we can just refer to it as n instead of like matrix at whatever row at, you know what I mean, dot length. So we're just going to say m is matrix dot length and n is matrix at 0 dot length. Okay, and then now we can start doing our binary search. So we're just going to start this off as usual. So left is 0 and right is going to be m times n minus 1. And that is because normally we would create the right, initialize the right to be array.length minus 1. But in this case, we're doing it based off of our imaginary array. So the length of this imaginary array is going to be the number of rows and columns from the 2D matrix minus 1. So we have 3 rows, 4 columns. So 3 times 4 is 12, and then 12 minus 1 gives us 11. So that is going to be the last element here, which is 11, right? So let's just make a comment that this is 11, this is 0 to start out with. Okay, and then we're going to do our while loop. So while left is less than or equal to, apparently I can't type today. While left is less than or equal to right, then we need to define our midpoint, which is going to be left plus right minus left divided by 2, as usual again. And so this starts out as 0 plus 11 minus 0 divided by 2, which is basically just 11 divided by 2, which is 5 if we do integer division, right? So, oops. So I'm just going to delete the conversion and just put 5. Okay. And then we are going to figure out, so the element at index 5 in the 1D array is going to be 11. So now we need to figure out how we're going to get 11 from this matrix. So we need to figure out the row and column for that element. So we're going to say row is, and we're going to do our little calculation here, which is going to be mid divided by n, right? Because mid in this case would be our index I that we are looking for. And then that is going to be 5 divided by 4, which is 1. So our row is 1, okay? And then we're going to do the same thing for column, except it's going to be mid mod n, which is going to be 5 mod 4, which is 1. Okay. So now we can check if that value here is equal to target, or if it's greater than or less than, right? And act accordingly. So just like how we would in a normal binary search. So if matrix at row at column is equal to target, then we can return true, because we're just returning a Boolean here, like if we could even find it or not, right? So we'll just return true, because if it is target, that means we found it. So otherwise, it's going to be either greater than or less than, which means we didn't find it yet. So matrix at row at column is less than target. So that would mean that the target is greater than it. So it'd be like in the right half of the array, which is not the case in this case, but let's just write this out. So if it is greater than the element at the midpoint, that means we need to cut out the left half of the array. So left is going to be equal to mid plus 1. So left is mid plus 1. Else, that means the target must have been smaller than the midpoint, so we cut out the right half of the array. So we just do the opposite. So right is mid minus 1. Okay, and then we can like walk through. So like in this case, target is 3, so we would actually do the last step because the element at the midpoint was 11, which is greater than our target. So right will become mid minus 1, which will be, mid was 5, so the right will become 4. Okay, then when right becomes 4, then we we iterate through this loop again. Left is still less than or equal to right because 0 is less than or equal to 4. So mid is going to be the midpoint of these two. So if we just calculate it, 4 divided by 2 is 2. So row is going to be 2 divided by 4, which is, row, I mean. So let's see, mid is 2. So it's going to be element 5, which is going to be, okay, so row is 2 divided by 4, which is 0, and then remainder 2. Let me just, yeah, that's correct. Okay, so then matrix at row at column, which is 5, is not equal to target, so we keep going. It is greater than target, actually, so we will do this one. So right becomes mid minus 1. And our mid is currently 2, so right becomes 1. Okay, and then 0 is still less than or equal to 1, so we continue, and then mid is going to be the midpoint of 0 and 1, which is 0. 0 plus, yeah, so it's 1 divided by 2, which is 0, yeah. So it's 0, okay, and then row is going to be mid divided by n, so that's 0 divided by 4, which is 0. Then the column is going to be 0 mod 4, which is 0. Okay, and then, so we check if the element here is greater than, less than, or equal to target. The element at 0, 0 is 1, which is less than our target, which is 3. So since it's less than that, we will do left equals mid plus 1. So mid is currently 0, so left becomes 1. And then 1 is less than or equal to 1, so we will continue. So mid will become the midpoint of 1 and 1, which is just 1. Then row will become 1 divided by 4, which is 0. And then column will be mid divided by mod n. So 1 mod 4 is 1. Okay. Now matrix at row at column. So row is 0, column is 1, so at 0, 1 is 3. So we can check, is that equal to target? Yes, 3 is equal to 3. So we have found it. So now we can return true, and then that is that. So if in the event that we don't find it though, then that means we will have, I'm not going to go through the entire thing because that would literally take like all day. So like let's say we go through this entire thing, we don't find it, then at the end we're just going to return false. Okay. So that's basically it. If you want, you can walk through again with example 2 where we wouldn't find it, but I feel like this video would literally be like 2 hours long if I did both examples. All right, so that worked. And then our time complexity. So let's walk through each of these steps actually. So, okay, well actually there's not really that much to walk through. We're just like, it's literally just like this while loop because everything else is constant. And this while loop is just doing the binary search. So for a binary search of the matrix, which is m times n dimensions, is just going to be O of log of m times n, where m is the number of rows in the matrix, n is number of columns in matrix. And then our space complexity is constant because we didn't use any additional data structures. Like if we created this array, like actually created it, then it would be m times n, but we didn't actually create this. We just like sort of used it in our imagination. So yeah, so the space is able to stay constant. So that's it for this problem. Thank you guys for watching. If you found it helpful, please like and subscribe, and I'll see you guys next time. Bye!